Folks, so here is the video for 2.6, the section called a numerical section. So before we begin this section, I want to start with some things that we know. And unlike the previous lists of what we know, these sections actually go back to maybe Calc 1 or Calc 2. So they're not necessarily things we've learned in this class, but maybe things that you saw at some point in your calculus class in the past, okay? So let's start with linear approximation. Linear approximation is just an idea that we can have a curve. So we can have, let's say, a curve that looks like this. And if we wanted to find the value at a specific point on here, maybe we could say like right here, we wanted to find that. If we use a tangent line and we draw a tangent line, okay, tangent line equations, because they're linear functions, tend to be a lot easier to compute. Whereas something like the blue curve, that could be cubic, it could be a fifth degree, it could be some other odd function, or it could be a combination of some other functions, right? And so the computations get a lot more complicated when we have a curve versus a line. And so what linear approximation is that we can estimate values using a straight line. So if we know the value at the pink point, and then we say, hey, what is the value at this green point? Instead of following the blue curve, we could say it's about this value on the tangent line. And so we use a tangent line to say we can get really close to the value we want. And that is why we call it linear approximation. We approximate values with a line. Okay. Now, the second type of approximation that you may or may not be familiar with is something called Newton's method. And what is a little bit different about Newton's method is that it is iterative. I had to think about how to spell that for a moment, but it's iterative, meaning that you do this more than one time, this process of Newton's method. We go through it more than one time so that we can get a better and better approximation. And we can use Newton's method to find quite a few things, but in particular, we tend to use this method to find what we call the zeros or the x-intercepts or the roots of a particular function. And so we might have a curve, something like this, and we know that it crosses the x-axis at a certain value, right? In particular, we can see it crosses right here. But what Newton's method does is it says, let's start off with one point. Maybe it's like somewhere here. And maybe that's a really nice value on that particular function. And we're going to use the idea of a tangent line to find out where that line crosses the x-axis. And then we're going to use this new x value, and we're going to say, oh, that x value is about here on the curve. So we go up from the x-axis of the pink line to find a new point on the blue curve. And then we do this process again. So from the orange line, we sketch a line, a tangent line, and we say, where does that tangent line cross? And from there, we go up to the y value on the curve. And if I zoom in here, I'm going to draw one more of these. All right. So we again find the tangent line. Where does that cross the x-axis? And you can see that with each iteration, my lines cross the x-axis closer and closer to where the blue curve crosses, right? So every time we use this process, we get closer and closer until we should get very close to the exact value at some point, okay? So all that learning of derivatives and tangent lines in Calc 1 were really to set us up to say, One application is that we can use lines to help us approximate values on curves that might be harder to find, okay? So again, the difference here is a linear approximation. We just choose one point, whereas Newton's, we repeat the process multiple times, all right? And so what's new? Let's take a look at what we're going to look at in this section. So our question is, how do we approximate solutions to differential equations that are not linear, separable, or exact? Okay, and so it turns out we're going to see a variety of differential equations, maybe not in this class, but there are so many other kinds outside of this class that maybe aren't as straightforward to solve. And in fact, there's a whole class, usually a 500 or 600 level class called numerical solutions to differential equations. And those classes use a lot of computing power to help solve equations that maybe by hand, by algebra, are very, very hard to solve, okay? There's a whole field of studies all around that. And so we're going to start to look at one method that really blends the linear approximation and Newton's method. And we're also going to ask ourselves, well, how accurate are these approximations? Okay, so we want to know not just how we can approximate something, but how close is that going to get us to our actual answer? All right. So we're going to use a little bit of technology in this. We're going to do a little bit of algebra. And for our homework assignment, the question on your homework, I believe it's question number 6 on homework number 2. You can use the link that I put on Canvas to help you compute those values. You do not need to compute them by hand, okay? Because I just want us to understand the process and not be stuck with the calculator trying to type so many decimals over and over again, okay? All right, so let's take a look at the concept. All right, I'm going to start with this differential equation, y prime plus 2y equals 2 minus e to the negative 4x. And we have an initial condition, y of 0 equals 1. And what we're going to do is we're going to solve this first using methods that we already know. Okay, so this will be a good review for the exam 1. We're going to solve this with methods that we already know. And then we're going to see, using this method, what answer do we get for a particular value. And then after that, we're going to approximate it using this Euler's method, and we'll see how close we get with our approximations. Okay. So this differential equation, if we look at this carefully, I see that it is a first order because it is a y prime. And I see, in fact, that it is a linear differential equation. Okay, and so that'll be something important to take a look at when you study for your exam next week. How do you know that it's linear? How do you know that it's exact? How do you know that it's separable? Okay, and so knowing that this is a linear differential equation, we are going to go ahead and find our p of x so that we can find our mu of x, or that magical multiplying factor or the integrating factor. Okay, so p of x, if I look at my equation, is just going to be the function that is the coefficient of the y term. So p of x in this case is 2. And we can find mu of x by setting e to the power of the integral of p of x dx. And in this case, we get e to the integral of 2 dx, or e to the 2x. All right. So we found our mu. We're going to take our mu and we're going to multiply it into the differential equation. So we'll get e to the 2x y prime plus 2 e to the 2xy. And before I write the other side, in my head, I do a quick computation and realize this left-hand side is the derivative of a product, and that's good, okay? So we can kind of see here, we've got one function, and that derivative is 2e to the 2x, right? That's good. And then a second function, and its derivative. And on the other side, we're going to multiply in our e to the 2x. We'll get 2e to the 2x minus e to the 2x e to the negative 4x. Okay. Now, with these last two terms over here, because I am multiplying these, I'm going to go ahead and add the exponents. And because there's a built-in negative sign, I'll end up doing 2x minus 4x. Okay. So I'm going to pack up this left-hand side, and I'm going to combine these terms together in the same step. Okay. So the left-hand side gives me dx of e to the 2x times y. And on the right-hand side, I have 2e to the 2x minus e to the negative 2x. All right, now we're going to integrate both sides. So when I integrate the left-hand side, the derivative goes away. And when I integrate the right-hand side, I realize I'm going to do a little bit of u sub in both terms. So I get e to the 2x times y equals e to the 2x, and then I get plus 1/2 e to the negative 2x. And we really, really, really don't want to forget that plus c. Okay. So we have a situation where we found our integrating factor, we multiplied it through, and we're able to solve this differential equation into the general form. Now we have a initial condition, okay? But it's also not too bad to turn this explicit solution into an implicit solution. So because we're going to be comparing this with other solutions, I'm going to go ahead and make this an explicit solution. All right, so before I plug in any initial conditions, let me make this explicit by dividing through by the e to the 2x. So I'll get y equals 1 plus 1/2 e to the negative 4x plus c e to the negative 2x. Okay, so I have to divide every single term by that e to the 2x. And now I'm going to go back. I'm going to grab that initial condition, y of 0 equals 1. Everywhere I see an x, I'm going to put 0. Everywhere I see a y, I'm going to put a 1. So I get 1 equals 1 plus 1/2 e to the negative 0 plus c e to the negative 0. And let's see, e to the 0 is going to give us 1. E to the 0 is going to give me 1. And so I end up with 1 equals 1 plus 1/2 plus c. And so from here, I get that c equals negative 1/2. Okay. So we have solved our linear differential equation. We found our c value, but what I want to do now is write a final answer where I have the c as a number. Okay, so let's not forget to do that part. So let me actually go back up to that line where I had the, whoops, not that one, this one, where I had my explicit solution. And instead of having a c, I'm going to put negative 1/2. And so I'm going to get y equals 1 plus 1/2 e to the negative 4x minus 1/2 e to the negative 2x. And this is my solution. Okay. Now, once I get this solution, I want to ask us another question. Okay. So the second question I want to ask us is, what is y of 0.2? And what I mean by that is, what value is y when I plug in a 0.2 for everywhere I see an x? So that means I have, let's continue in the blue, y equals 1 plus 1/2 e to the negative 4 times 0.2 minus 1/2 e to the 2 times 0.2. And once I put this into the calculator, I get a whole long string of decimals. I'm just going to truncate to the 5th decimal place. I think that's enough to show us when we compare to our approximation on the next page. Okay. So when you put this into your calculator, you should get 0.8895. If you grab all of them, you've got 4459041. But for the purposes of this, let's just focus on the first 5 decimal points. Okay. All right. So, whoops, here it is all on one slide for you. We solved this, we found our solution, and we used our solution to give us an exact value. Okay, so this is our exact value of when x equals 0.2. All right. So this question was all fine and good because it was one that we knew how to solve, right? But the whole point of approximation is that sometimes we won't be able to solve things. And so what we're going to do next is we are going to approximate the value of what happens when x equals 0.2 without solving this differential equation. So without doing all of this, we're going to approximate a value for y of 0.2, and we're going to see how close that gets us to this exact value. All right, so now we're going to use Euler's method, okay? And we're going to use this twice. The first time, we're going to use h equals 0.1, okay? The second time, we're going to use h equals 0.05. Now, let's make a note here that h is 0.1. This is the step. This is how much I'm increasing by to get from my initial condition to the point that I want, okay? A step of 0.1 is smaller or is larger than a step of 0.05. And in particular, the first step is twice as big as the second step. And so if we think logically, which one do we think will give a better approximation? I hope that we say the second one because we are sort of cutting it into smaller pieces as we approximate. Okay, so we're able to get closer and closer to the actual value. Now, you'll also notice there is a table for the first one, and there's no table for the second one. And that's because I want us to try doing this by hand one time with the table, just so we kind of understand what's going on. And then for the second one, we're going to use the link that I provided in Canvas. We're going to type some things in there, and it will give us the actual or the approximate value when h equals 0.5. Okay, so we're going to do a little bit by hand to get the idea of the process, and then we're going to go ahead and use technology, because the reality is you won't ever be calculating these by hands. You will 100% be calculating these using technology. Okay. All right, so if we go back to our differential equation, we have this, okay? And if you look at the things that we want in our table, I'm asking for dx and dy dx. And so one thing I just want us to remember is that dy dx is the same as y prime. So in my differential equation, if I get y prime by itself, and then I plug in values for x and y, I'll be able to get my dy dx. Okay. I'm going to take a moment and rewrite this differential equation here. I'm going to write this as y prime equals 2 minus e to the negative 4x minus 2y. Okay, so y prime equals 2 e to the minus e to the negative 4x minus 2y. And that, if we keep with our color coding, this will give us our dy dx. Okay. Now, the idea behind Euler's method is that we start with a point we know, and oftentimes this is a nice point. And in particular, we start with our initial condition. And so our initial condition was 0 for x and 1 for y. Okay. Now, I'm going to go ahead and make the 0, highlight that in a yellow, and the 1 I'm going to highlight in a green. Okay. And so what Euler's method means is that we're basically going to add a little bit to the x and add a little bit to the y and get a new point. That's what this whole first line is going to tell us. All right, so we're going to add a little bit to the 0. We're going to add a little bit to the 1 using what it means to change a little bit dx and dy. And we're going to get a new point at the end. Okay. Let's go ahead and practice this process, and then I'll tell you what we're going to do with the second line. So dx means how much are you changing your x by? That happens to be the same as your step. And so for dx, I'm going up by 0.1. Okay. Now, if we sort of think ahead, we might notice that at the very last one, I wrote x plus dx, because I'm going to take the yellow, I'm going to add the 0.1, and that will be my new x value. Okay. So if we continue with the color coding, this will be in yellow, and I'm going to add them together. So 0 plus 0.1 is 0.1 to get the new x value. All right. Well, if we're going to add a little bit to the x, we have to add a little bit to the y as well. And how do we know how much to add to the y? That depends on the differential equation. So we're going to take our x and y values, we're going to plug them into this equation, and that will give me my y prime or my dy dx. And so if we do a little mental math here, we've got 2 minus e to the 0 minus 2, and that gives us 2 minus 1 minus 2, or negative 1. And so this negative 1 is almost my dy. That is my dy dx. Okay, so let's actually not make that green. Let's keep it in that reddish color. If I only want dy, because I only want to add the change in y to the y value, well, it turns out I can work with the dx's and the dy dx's kind of like fractions. And so I can take my dx times my dy dx just to get dy. In other words, if I multiply my yellow by my red, I will get the change in y. And so when we multiply these, we get negative 0.1. And this I will color in the green because that's what I'm going to add to the original y value to get the new y value. And when I add those, I get 0.9. Okay. So by using this, we're almost drawing a slope field, like those arrows on the slope field. We are drawing an arrow that happens to be 0.1 in the x direction. Okay. So now we found this new point, 0.1 and 0.9. And because Euler's method is iterative, kind of like how Newton's method, if we go back up to the top, with Newton's method, we did one line and then another line and then another line, and we kept going until we got close enough. We're going to do Euler's method with iterations as well. Okay, so we're going to actually do this 2 times. So I'm going to grab the ending value, 0.1 and 0.9. Let's color code them accordingly. And let's figure out our new dx, dy dx, and our dy so that we can end up with a final value. Now my step is set as 0.1. So my dx is still going to be 0.1. My dy, well, if I want to find dy dx, I'm going to take 0.1 and 0.9, and I'm going to plug them in to the differential equation for x and y. I won't bore you with the calculations of that, but please try that and confirm that it's negative 0.47032. Okay, so again, I got that value by taking 0.1 and 0.9 and plugging that into the y prime equation. But in order to find my dy, I need to take dx and multiply it by dy dx. So I'm going to take this yellow and this red and multiply them. And when I do that, I get negative 0.047032. And this is the change in y at the new point given the change in x at the new point. So now let's find the new point. We're going to take yellow plus yellow, green plus green, and we end up with 0.2, comma, 0.85297. All right. Now, before we compute the step where h equals 0.05, I want us to look at this number real quick, 0.85297. That is the y value when the x value is 0.2. That's an approximation. When we solved for the exact value, we found that it was 0.8895. So 0.8895 and 0.85297 are kind of close, right? It's not that far. It's not like I got 18 million as an answer, right? These are fairly close decimals. And I did this with a step of 0.1, okay? We're going to use technology now to find the approximation when we do h equals 0.05. Let's see what value we get there. Okay, so I'm going to switch my screen share. That's a challenge. I've not done that before. Okay, we're going to stop sharing. We're going to reshare. And hopefully you can see this as the Euler's method calculator. Okay. And so when you go and try this, you're going to go to the link that I put in Canvas, and we're just going to follow the directions. Okay. The first one says enter a function, and it says y prime equals. So we do have to solve for y prime. Okay. So I went ahead and I typed in my y prime, and let's make that an x. All right. So this is the same equation that I solved for before I started plugging numbers in. It says enter the step size, and I put 0.05. It says enter the initial condition, so I typed in 0 and 1. And what am I finding? I want to approximate y of 0.2. All right, so you type that all in, you hit calculate. It will think very quickly, much more quickly than we could do it, and it will show you the approximation after each step, okay? So after one step, we get 0.95. After another iteration, we get this very long decimal. After a third iteration, we get this decimal. After a fourth iteration, and we get to an x value of 0.2, this is our y value. Okay. So let's go ahead and write that down. All right. So for your homework, if you are handwriting it, you do not need to write out each step. But what might be helpful is if you just write things like this for me. Okay. So the coordinates of what you're getting. So we start with 0, 1. If I step up by 0.05, then what was that y value? Let's go back and grab that. That was 0.95. If you add another 0.5 or 0.05, you get 0.1. And then that would correspond to this y value. So I can write 0.91. I would say 4 decimals is enough, or 5 decimals, sorry. So 0.91406. All right. What comes after 0.1? If I add another 0.05, I get 0.15. And so that would be the y value from here. And that is 0.88914. And what happens if I add another 0.05? I get 0.2. Now that's the x value I'm looking for. So that's how I know I'm done. I get my approximation here, 0.87279. Okay. And so we won't be able to color code all of these. Whoops, I realized this one should be a yellow. We won't color code all of these, but we should recognize that each one of these pairs will be green and red, or green and yellow, okay? So let me switch back to the other screen so you can see what I was talking about. All right, so I've written out the pairs that I had from the calculator online. And so each one of these pairs, this is the x value, and these are the y values that go with them if we plug each point into this y prime, okay? And so what we are interested in is the 0.2 x value. So we've got this one and this one. Okay, so we're going to finish this lesson by comparing that to the exact answer. All right, so I'm going to write down the exact value that I got from before. My exact value was, what was it? That 0.88950. Okay, so that is my exact value. And now I'm going to find the percent error when I used only the first 2 iterations, so a bigger step. And so we're going to take this formula, percent error equals the difference between the exact and the approximation, and divides it by the exact value, and times 100 to get it into a percent. And we should end up with 4.107%. So it's a less than 5% error. And it only took us 2 steps. Okay, so is that good enough? I don't know. It would depend on your particular situation. Okay, but let's see what happens when we just cut the step in half. So we're doing it twice as many iterations, and let's see how that compares to our percent error from the first one. our percent error is going to be 0.88950 minus 0.85. Nope, wrong number, Judy. I want to take this one, the 0.871, so 0.87279. And I'm going to divide it by the exact times 100. And I won't bore you with the calculator, but double check my thinking. We should get, what did I get here for this error? We should get an error of 1.879%. Okay. So we were able to get so much more of an exact answer just by making the step count half the size of what it was. And so if you can imagine running through this through a program, a computer program, right? If we have the technology and we can make this step as small as possible, computers can run all of these computations so quickly that if you can make the step smaller, you can actually get a more accurate answer pretty quickly, okay? Now, it's probably a fine balance. You don't want to make the step too small because the computer might take forever to process your data. So as you think about like a percent error, it would be important to think, what is important for this particular project that I'm working on? How accurate do I have to be? Those are all good things to think about. And you can find sort of a sweet spot where you can still get a fairly accurate answer without slowing down your computer program too much. Okay. And so that is the story of Euler's method. All right. So a way to approximate, it kind of blends this linear approximation and Newton's method using slope fields and using slope fields, but having lots of iterations of those. So the smaller we make those arrows, the more accurate our answer will be. Okay. So I hope this was helpful. Let me know if you have any questions, and I will see you folks tomorrow.